As you can see, I had to get a bit of a goofy getup on to get into the mushroom house. Makes sense. In order to keep things sterile, you have to keep the bacteria that might be on your body and your hair from getting into the mycelium beds. It keeps them nice and fresh to get onto your dinner table, so that's important. The people of Kennet Square figured out how to make a pretty good living off of recycling waste into useful products. The village is beautiful, and I suggest that you stop in if you're going through Pennsylvania. But let me step back for a moment and talk about the concept of recycling. Many of you are probably thinking, aren't we effectively using all of our wastes today when we recycle? Well, this is not really true, and the recycling symbol itself might be a big reason why we think this is so. Let me simplify the symbol a bit for the purposes of argument. Looking at this, it seems that everything, once used, is then moved on to the next step of the process. But if this were so, we wouldn't have to mine anything new, because we could just reuse old things. The fact is that there's a lot of waste in the way that we handle our waste. Every step of the process produces waste and uses energy, and so even the recycling process requires a lot of inputs. The challenge we face as a society is closing this circle and creating a system of waste management that truly uses everything that is discarded, either to create new useful things or to create energy to put back into the cycle. If we could manage this continual act of transmutation and truly use everything that we now consider waste as resources, we would go a long way towards building a sustainable future for ourselves. Now, this isn't a fully closed loop, as there's always one energy input that functions without ceasing. That is, our sun. All of our energy, in the end, comes from the sun. Even the fossil fuels we burn and the nuclear power we harness has, as its source, that great burning sphere. In the end, the real key to using everything is harnessing new sources of power and increasing our efficiency in using them. You might say that this new symbol of the challenge ahead of us looks like a flower. Well, this is not an accident. Consider it a form of biomimicry. One of the things that inspires me as a scientist is the idea of biomimicry, the idea that we should look to nature for examples of how better to engineer our society and our infrastructure. Well, nature has a really ingenious power generation system, and it's called the plant. And plants are great because each of these leaves is like a tiny generator that's producing the energy that is needed for the plant to survive. Well, imagine if a plant were engineered like our system. It would have just a few very large leaves, and these leaves would be responsible for providing energy to the entire plant. And as it went along the branches and into the roots, a lot of that energy would be lost because you have to keep those tissues alive. In much the same way, our energy system loses 40% or more of the energy just in transmitting it from point A to point B, because we're relying upon a small number of very large generators, when we should be relying upon a much larger number of smaller generators. And a good first step to getting this done would be to build many facilities like they have here at Cowpots, to gather methane from sewage treatment plants, from landfills, and from farms. And then take that methane, run it through natural gas generators, and turn it into electricity. And the great thing about this is if you mixed in with a little bit of solar, a little bit of wind power, you could have energy everywhere. And that energy wouldn't have to travel very far before it could be used. And as a result, the amount of energy we would lose to transmission would fall to nearly zero. So that would be an energy savings of 40% right off the bat. Imagine how much money we could save if we just get rid of our energy transmission problems. I'd like to introduce you to the power plant of the future. You're looking at it. It could be your house, and there's good reason for this. You see, one of the major inefficiencies of our society is that we have these power plants that are transmitting electricity over very long distances. And as a result, we're losing 40-50% of the power right off the bat just from transmission. If we were generating the power ourselves at home, those transmission losses disappear. And like I said, if we designed our society like a plant with many places that are generating power, then we get rid of a major inefficiency and we can increase the amount of energy that's available for everyone to use. Now, this house, which is the Meso House at the University of Michigan, was designed for the Solar Decathlon back in 2005. Now, those of you that have been paying attention, they've been doing these solar decathlons every year and they keep getting better and better with even more amazing designs. But I think that this one is a good example because it's very buildable given today's technology. The solar panels, the solar collectors for the water heating, all of this stuff is right off the shelf nowadays. So you could actually build this house yourself for a relatively small amount of money. And in doing so, you'd have a house that's actually producing a positive amount of energy. In other words, it's actually dumping energy onto the grid instead of collecting it, at least most days. And in those days where you don't have much sun, there's enough stored in the batteries so you can keep yourself going for a while. So let's see how this is from the inside. tell me a little bit of history about the Miso House.
Well, the Miso House started off before 2005 as a project, and the project was between different disciplines in the University of Michigan. So you had the School of Architecture and other schools involved in the design of this. They were all part of a project that had to look at not only the living quarters, but how would you manufacture this? And what would be some of the best practices you can employ to get the efficiencies that were part of the contest rules, to be exact. So the house was designed around that set of rules and regulations. One of the things is it had to be mobile. So if you looked at the way this is structured, it's actually 5 pieces. And the pieces themselves are capable of being unbolted and trailered very easily. The structure has built into it capacity for axles to put tires on it, and this could be trailered by just a 5th-wheel pickup truck and take it wherever it has to be. Bolted back together, lag down onto some kind of foundation, and you have an instant building ready to go.
So what other structural accommodations have you made for the solar array?
In here, we start off up on the outside. We have our solar cell arrays. They generate a DC voltage, and it's a stacked voltage because there's arrays are set up in series and parallel. So it's going to generate the power. That power comes back to a unit that's sitting back here, and maybe for your purposes we'll pull this away so you can see what that is.
That would be nice. I can cut that in later.
I was saying we could do that, but in general what happens is the voltage or the current's coming down from the solar cells, and it goes to an energy management station. That station changes the voltage level because it's a little on the higher side up here as it's being generated. But we want to be able to store it, and we do that in a set of batteries that are located here all the way along this hallway in here. If you look at here, there's access panels. And those access panels go to a bank of 72 cells. And I should say actually 72 batteries, because they're more than just a cell there. And that gives us a reserve for approximately 3 to 5 days worth of no light whatsoever on the solar cell. So we actually have quite a bit of power reserve sitting here. And that's what gets us through the nighttime and, of course, when there's diminished sunlight. At some point, you know, if you were to discharge the batteries fully and there wasn't enough sunlight, then you might want to have to draw power in off the mains. So from a safety standpoint, in the wintertime, it might be prudent to have an actual electrical connection. The advantage of this system is that any excess that you're drawing in actually gets put out on the main, so you can actually build up a surplus. And then in the wintertime, draw against that surplus.
A big part of the reason that the Miso House is so efficient, indeed it is able to produce more energy than it uses, is the way that it efficiently uses the energy it takes in to keep its occupants comfortable.
Cold air is drawn up into these chambers. These chambers exist along the entire ceiling, and they're sealed area with an opening in the bottom and an opening in the top. And basically as the sunlight strikes the surface of the building here, it heats up that chamber, and that chamber causes the air to rise, and in the act of rising it draws in cooler air, and it's a continuous process. So in a sense it's like an active insulator. It's taking away the heat that normally would have been deposited inside the building and letting it go outside. Of course that's the summer show. That does happen in the wintertime, but there we actually don't want to lose the heat. We close off the vents at the top and the heat's actually pumped down this way. So that's one form of how we manage the heat. Another form in here is the flooring is ceramic tile. And the ceramic tile has underneath it a set of tubes. And solar water heated fluid is passed underneath the tubes. And those tubes in turn now heat the ceramic tile, and the ceramic tile radiates the whole building. So one thing you'll see in here is this unit does not have furnace fans or anything like that. The heating is distributed, and because it is like that, it relies just on the convection off of the materials to give the distribution of that, which makes it kind of comfortable. You don't have the noise of fans and other things.
It's also more spatial.
Oh, it's very spatial. I can walk over in that corner and it won't be cold because that flooring right there is just as warm as it is where I'm standing over here. So
Indeed.
That's one thing. There's material in here that's used. Instead of a normal gypsum board in here, this is a polymer and actually a sandwich of materials in here that are special properties. Each one of those gives us a little different thing. Fireproofing, or an insulating characteristic. So that actually forms part of this chamber. The outside skin of this building is aluminum. Mm-hmm. And the aluminum, of course, has its reflective properties. So you have the same type of thing you would see off of any kind of reflecting material. A piece of aluminum foil reflects the heat. This does too. And also, it's structurally strong. So what we have in here is not only a skin, but also a framework, and it's all welded together. It's in what's called a monocoque construction, and that is very, very strong.
So very much like a modern automobile.
An automobile, and actually like an airplane. Airplane was where you first would have seen this. So, and that, you know, it's a little stylistic. The aluminum can be shaped and formed in, and it could be made the kind of structure it is. This actually has an aerodynamic structure to it, too.
Indeed, it's curved enough that if you set into the prevailing wind, it probably would not experience any major problems like
that is correct.
A normal portable
unit would. It really is. It was, that's part of the design requirement, was for some of the aerodynamics. But also the other thing is, we're looking at the side of the house that faces to the sun. You notice that this slopes off it this way, and that's because that's where our solar cell array is.
If everybody had a house like this, you could have a localized energy grid where you wouldn't be losing nearly half of your power just transmitting it from point A to point B.
That is
because it wouldn't be going
correct.
Nearly as far before
there
it's
is
used.
No transmission losses. There are minimal transmission losses in the building. If you look at the distances we have to cover and the amperages we're talking about here, the losses are minor. If I go put that out on a power line, even at 345,000 volts, there's still a significant loss over miles of running the three-phase.
Indeed.
So, but basically, let's go continue, because we're not done yet, as they say in the commercials, but there's more. And the key thing here is that not only do we save the power here, we have enough solar cells up on deck here that part of the contest design was to be able to have yet more power to charge a battery-powered car. So this thing, and that's one of the reasons why it has such a high surplus in it, is you can also charge a car here. Mm-hmm. So we have that capacity in the system. But we also have it so that you would be very much feeling at home 120 volt normal house circuits. And that's done by taking the battery voltage and running it through an inverter. And the inverter converts it back into 120 volts AC, taken it from the battery's DC voltage, and makes it so that all the appliances that you see here could be standard off the shelf. They don't have to be special, which makes that kind of nice too, because now we're back into commercially available equipment as opposed to specially available equipment.
So about how much would it cost for an individual to build a house like this, given the materials that are available today?
Well, there's two ways to look at cost. One is in mass production, and one is, as you just posed the question, as an individual would do this. Probably from the individual side of things, you're at the $120,000 plus level. But if this was mass produced and done with jigs and fixtures and prices brought down near the commodity levels that they should be, this could go for as low as $80,000.
It's not
so at pricing for what you're getting, and that would include, at least according to estimates that we have here, the all the solar equipment plus all of the appliances. So that's actually a pretty good deal. If you look at the net life of most of the equipment in here, solar cells, probably 10 years. While this isn't infinite, it certainly has a good payback.
Creating energy-positive homes is a great first step towards building a sustainable and energy-independent future. But we also need to consider how we might start using the resources at hand to create energy everywhere it is used. For instance, this cellular tower has a solar array pitched near it that produces more power than is needed by the antenna system. Similarly, recreational structures in our parks and cities need to be outfitted with energy generation devices. If we can accomplish this, then we will have plenty of energy with which we can process waste into useful things. And in so doing, we can close the circle of our society and create a culture that can continue functioning indefinitely without destroying our planet in the process.
The sky calls to us. If we do not destroy ourselves, we will one day venture to the stars.